Da última vez, deixa eu pensar. Sim, antes de começar um anúncio. Próxima terça-feira, dia 20, é feriado. Então a gente não vai ter aula. Fundação do Estado do Rio de Janeiro. Feriado municipal. Não, Fundação da cidade do Rio de Janeiro. Então, isso quer dizer que, como a gente vai ter uma aula a menos antes da prova, se estiver tudo bem com vocês, a gente vai mudar a primeira prova. Do dia 27 para o dia 29. Tá bom? Porque senão a gente não vai ter material suficiente para a primeira prova. Tá bom? O que mais? This is for you. So the lecture will still be in English, but I'm going to make all the announcements and stories and etc. in Portuguese because some of the students are not super confident in English, and sometimes they don't understand exactly what I meant to. So the first exam, it goes from 27 to 29. Okay? So last time what we did was to define what is actually a Markov chain in a mathematically rigorous way. I stated without proofs a theorem for which you need the measure theory that says that given a state space omega, an initial law mu 0, and the transition matrix P, there always exists a Markov chain with these three parameters, with state omega, measure mu 0, and transition matrix P. Okay? So we're not going to worry anymore about the existence of Markov chains. We're going to move forward. Okay? So for the moment, the examples of Markov chains that I gave you were what we call symmetric simple random walks. Okay? So you take a graph, for example, let me take as a graph today Z, okay? So the integer numbers and the simple symmetric random walk here just jumps to the left and to the right with probabilities 1/2, 1/2. So now we can introduce a new example, something that people call the asymmetric simple random walk. Okay, A from asymmetric, S from simple, R from random, and W for a walk. And what the asymmetric random walk does, it jumps to the left and to the right with probabilities P, and Q equals to minus P, where P it's a number between 0 and 1, and p is different from 1/2. Okay? So here I'm excluding the degenerated cases p equals 0 and 1, because in those cases this random walk is not fun, no? Because it's just deterministic. It goes at each step, one step to the left or one step to the right. Okay? So it's not a very fun random walk, so we're not going to consider it. Okay? So in general, given a graph, what we call simple symmetric random walk is the Markov chain that at each step jumps to a neighbor of where it is with equal probability. Okay? So it chooses one neighbor uniformly at random and jumps to that neighbor. So this is most of the time when we use the word random walk, we're referring to the simple symmetric random walk. When we want to be more specific about it, we call it simple symmetric. Okay? The word simple means you can only jump to your neighbors. And symmetric, well, symmetric. And asymmetric, not symmetric. So you can build your own examples on any graph of non-symmetric simple random walks. Okay? You just take a graph and you decide to jump to one of your neighbors with some given distribution. Okay? So let me introduce a further example of this asymmetric simple random walks. It's what we call random walks on groups. Okay, so here we have a problem because I had to write something like let G be a group, but G is a graph. So what can we do? Okay, so one possibility is to do different G's, no? But so let's see, how many G's do we have? So we have G, we have capital G, we have a small g. What other G we have? Maybe blackboard G. Maybe we have a calligraphic G. Which other G we have? Huh? G bar. Okay. Okay, so looking at these ones, I decided that the best solution is to do let V be a group. Okay. So what is a group? Remember, a group it's a set that I'm going to call V. I'm going to call it V because it's going to be this V in a few moments is going to be the vertex set of a graph. And then there is an operation, no? That you can call multiplication if you want, or maybe addition. Usually, the usual convention is that if the operation is commutative, we use addition sign symbol, and if the operation is not commutative, we use the multiplication symbol. That's just a loose convention about how to call the operation in the group, and a set is a group if. So this guy here is a group if three conditions are satisfied. No, the first one is associativity. Right, so is that x times y times z is equal to x times y times z. The second condition is the existence of a neutral element. So there exists an E in V such that E times x is equal to x times E for all x in V. Right? And the second condition, no, third condition, is the existence of an inverse. Okay, so for every, so now it's for every G, or what I call it x in V, there exists y in V such that x times y is equal to y times x equals to E. Okay, so this is a group. Okay, so here I'm going to add an extra condition. There's a non-empty finite or countable group. Okay. So what is your favorite group? It's not finite or countable. ¿O cuál es su grupo favorito?
Alguma restrição?
¿Ah?
Alguma restrição?
No vacío, finito o enumerável.
Não vazio, infinito, numerável?
No vacío, finito ou enumerável.
Os naturais?
Os naturais não é um grupo.
Inteiros. Ah, inteiros.
Tá bom. Which is your favorite group?
Zero.
Zero? Only 1 point, no, not super fun. Not my favorite. Which is your favorite group? Okay, so let me tell you what is my favorite group, okay? So my favorite group is usually denoted by Sn, and Sn is the group of permutations. Okay. So this group is super fun. Okay? All those groups that you were mentioning are super boring. Okay, so so we say that a subset B of V, yeah, that's correct, I think. So we say that a subset B of V is, let me write it like this, generates a V if for every x in V there exists a natural number L. Remember that natural number does not include 0, okay? So it's a natural number L, and B1, BL in B, such that X is equal to B1 times, okay, so people usually write it like this, BL times B1. Okay? So this means that the set V generates V. Okay, so it means that every so maybe I'm not going to call this example, but I'm going to call it another thing because it's going to be longer than just an example. Section. Okay? So the set, for example, the set plus 1 minus 1 generates Z, right? In general, the set plus minus EI, I equals 1 over D, generates ZD, where EI J is equal to 1 if J is equal to I, and 0 if J is different from I. Okay, this is called the canonical basis. So this is here, it's called the canonical. Of ZD. Okay? This set here also generates what does it generate? It also generates okay, so this is what people call usually the discrete torus. But it's just the it's just the integer vectors modulo n. Okay, so here if we consider, so here I didn't specify what are the what is the operation, but the operation is addition, right? So here the operation is addition, here the operation is a vector addition, and here the operation is vector addition modulo n. Okay, so these are some few examples, classical examples. Another important example is the permutation. No? So let Sn be the group of permutations. Okay? Okay, so every permutation is a product of transpositions. Okay, so if you learn, maybe you don't. If you remember, maybe you don't remember because you don't learn it. But if you learned about the group of permutations, sometimes they call it the symmetric group, no? I think that the S comes from that, no? Every permutation can be written as a product of disjoint cycles. And then every cycle can be written as a product of transpositions. Okay? So if you want to move everybody, so you put people on a circle. So this is this is the famous problem that of the boyfriend arriving to the table on a bar, no? So everybody's sitting on the bar, and then the boyfriend of someone arrives, and then you have to make room, no? So everybody moves one spot to their side, but you have to start from the last guy, no? Until you make room for the extra person. So this is how you actually can write a cycle as a product of transposition. So this is called a transposition, no? When you change only two elements, the position of two elements on this permutation. So this generates all permutations. This one here is a little bit trickier, but it also generates all permutations, right? So you can imagine you have a stack of files, and then you want to order in some way. So what you do, you want to put so there is a very lengthy algorithm, no? There are various algorithms because it's a complicated problem, but you can think about the simplest one, which is just, okay, so we need to get the right order. So we need to get one below 2. So you bring 2 to the top, and then you exchange it. You bring 2 to the top again, and you exchange it until you exchange 2 and 1. Then you bring 3 to the top, and you exchange until you do that. So you try to do that, and then you realize that this is not the way to do it. You have to do it from backwards. So you have to do it first with the n and n minus 1. Okay. But at the end of the day, you discover that these two guys here, they do generate the whole of Sn. So C, and maybe this one is more interesting. So you can imagine you have a stack of cards or something like that, and you want to put it in some order. You can always exchange the first one with some other one. So what do you do? So you look at the card which is on top, and you look at the position you want to put it, and you just exchange. And now you have another card on top, and you look at the position you want to put it, and you just exchange. So you can see that more or less easily that with at most 10 n of these operations, you can just sort a stack of cards in the order that you prefer. Okay, so all this is just to give you some let's say some canonical examples of generators of a given group, some non-canonical examples, and you can see here that the generators are not unique. sets of generators are not unique. They can be very complicated, especially if your group is non-commutative. Another example, which is it's a nice one. So the diedral group the n is generated by two elements, by two generators. AB, let's say AB, which satisfy so they satisfy three properties. Now the first one is that A squared is equal to E, and A is different from E. Okay. B to the n is equal to E, and B to the I is different from E for every, and let me assume that these guys are different too. B is different from E for every E smaller than n. And C, AB is equal to B, AN minus 1. No. It's the other way around. So, can you figure out which group is this? Huh? It's a group of symmetries of a regular polygon of n sides. So if we imagine this is a square, you can number 1, 2, 3, 4. So you see, it's the same to do this, and then this. You have to imagine that it's transparent, okay? So let me see. So do this and then this is the same as doing this and then this. Huh? So let me see. How does that work? Let me see. So A is reflection and B is rotation. That's the idea. So reflection twice, we're okay. And rotation 4 times, we go back. So this is rotation first and then reflection. You can see where this thing goes, no? You can imagine. It's the same as rotation first, no, reflection first, and then rotation, no?
You have to rotate 3 times, right?
Right. So I have to rotate it, but I have to rotate it in the right sense. 1, 2, 3. Okay? So you can have a lot of fun discovering that this actually generates a group of exactly 2n elements. So now the question is, why am I telling you about algebra, no? So probably if you came here during summer and you are sitting in the course on Markov chains, one of the reasons could be that because you really don't like algebra. Okay? Well, I have news for you. If you want to do research in mathematics, you have to learn as many different things as you can. In particular, sometimes a little bit of algebra is saves the day. So and now let's do the definition of what we call a random walk on a group. Okay, so definition. So let be a group. So this is going to be a group. Let so V be a finite set of generators. It could be countable. But we are not to discuss countable. Okay, we are only going to discuss finite set of generators. And let nu be a probability measure. On B. Okay, so a random walk on a group has three parameters. Okay, so the group, the set of generators, and a probability measure on the set of generators. Okay. Okay, so let me just explain what do I mean by BIID with common law nu. Okay, so IID means independent and identically distributed. Okay, so it means that you have a sequence of random variables on which all these random variables, they have the same law. Okay, so they are chosen randomly in the same way, let's say, and they are chosen randomly but independently. Okay, so the classical example of IID sequence is a coin toss. No, so you do coin tosses, and you always the usual assumption is that these coin tosses are independent among them, and they are identically distributed because you assume that probability of getting heads or tails is 1/2 always, no, at each toss of the coin. Another one is throw of dice, no. So you throw a dice in sequence, and what you get is a sequence of throws which is IID. So it's independent, identically distributed. The distribution, if the dice is well balanced, is just uniform. Sometimes the dice are not well balanced, and then the distribution is just uniform. Curiosity. Have you observed that the opposite sides of dice always add up to 7? You know that the reason for that is because otherwise the dice is not well balanced. Okay? So it doesn't mean that the dice is well balanced if you do that. But what is true is that certainly the dice is not well balanced if you don't do that, because then you are altering the center of gravity of the dice. So if a dice is done by usually the dice is done by taking a cube of wood or plastic and pinching some holes, no, on the faces, representing the numbers. So if the sums add up to 7 on each opposite faces, then you are pinching the same number of holes on each axis of the dice. Okay, so usually we assume that it's uniform, but here we're not assuming that this is uniform. And observe that the set on which these random variables live is not the set of is not a set of numbers. Okay, I'm choosing elements of a group uniformly at random. That may sound a little bit strange, but actually it's not really that strange. Okay, because whenever you choose something at random, you are choosing an object from a collection. Okay, and you can whatever object, whatever collection you can use it, you can relabel this collection to mean something else. And in this case, what it means is the elements of a group. Okay, so now that we do that, we did that, we can define the random walk. On V associated to new. Observe that I told you that a random walk has 3 parameters, and here I'm giving only 2 of these parameters. But actually, if I give you mu, I implicitly giving you also B. Okay? So this means that here I need to make an extra assumption, which is no, I'm not going to make an extra assumption for the moment. Okay? So why? Because whenever you give a function, remember that a function is not only a formula. Okay? A function is something that has a domain and how is called that the other guy? It's not the image, no? Codomain. Yeah?
E se elemento estiver isolado, por assim dizer, tipo, eu vou tentar formar um exemplo. Você tem o B seria como se fosse um círculo fechado, mas você também tem um ponto aqui.
Aí não seria um grupo.
Por que não?
Porque um grupo tem que estar bem definido. Como que você vai multiplicar esse ponto por carinha do círculo?
Para ser um grupo, você precisa existir de qualquer maneira de um ponto chegar até o outro por N passos. Não pode ter pontos fora. Seria isso?
Não, não necessariamente. Isso é uma propriedade dos geradores. É para ser gerador que tem que ter isso. Quando você tem um grupo, a princípio você não tem uma relação de vizinhança. associated to Okay, so what you do is that maybe well, sometimes you put the point, sometimes you don't put it, no? When you write down about groups. So we stick to the notation of not putting points there. So what you do is that you build this random walk in the following way. So you are at some position xn. Okay, so some position at time n. How are you going to choose the next position? You're going to throw some random generating system to choose one element of the set of generators, and you are going to multiply your current position from the left by that element, and then you are going to jump to the outcome of that multiplication. Okay? So, very surprisingly, most of the examples we already defined are random walks on groups. In particular, this one here is a random walk on a group, right? So the group is the group of integer numbers. The set of generators is plus and minus 1. And what we're doing at each step is that we're choosing plus and minus 1. In the symmetric case, we probably do 1/2. And we are adding to the current position plus 1 or minus 1. So to the current position, we're adding one of the generators selected in some random way. And this random way, so these generators each time are selected independently of what happened before. So, and for the asymmetric simple random walk, what changed is the distribution mu. The low mu there, the low nu, now is gives weight p to minus 1 and weight q to plus 1. So if you remember the examples we did last time, most of them were actually groups. No, what we did the integer lattice, the hypercube, the circle, the discrete torus, all of these vertex sets, they come with a well-defined operation that makes them into groups, no? In these cases were addition, no? Either addition, vector addition, addition modulo n, vector addition modulo n. Okay? All of them were groups. And if you remember, the notion of neighbor is exactly, we were saying that 2 points on these graphs were neighbors if the difference was, where are these guys? One of these guys here. So the random walks were all of them random walks on groups, okay? So, well, the Plaza de Armas is not a group. And also the complete graph is not a group. So we had a few examples of also of random walks which were not random walks on groups. Okay, so many examples are random walks on groups. Many examples are not random walks on groups. What is the why do we want to study random walks on groups? Because whenever you have extra structure on a given set, you can use this structure to compute things. Okay? So in particular, whenever you have a random walk on an abelian group, okay, abelian group means that the operation is a sum. The operation is commutative in general, no? There is a very powerful method called, you know what is the method that you can use to analyze almost everything that happens in this type of sets? Well, the operation is called Fourier transform. Okay? In this case, what is a discrete Fourier transform. And in computer science, we have something called FFT, no, fast Fourier transform, that allow us to compute very, very quickly Fourier transforms in discrete groups. Yeah?
Estou familiarizado com Fourier transformações Fourier para você identificar frequências constantes em um sinal. Eu não entendi como uma transformação de Fourier se aplica.
Tá certo que você não tenha entendido porque ainda não expliquei. So actually this is may or may not be part of what we are going to discuss in the course. Okay, so I'm just telling you, no, as a information, no, so you can learn about it if you want. You can find it in the literature that for random walks on groups, we have the powerful machinery of Fourier transform to allow us to do some analysis of these Markov chains. So just a hint into how this entered into the game is that this guy is going to be we are going to prove that this is actually a Markov chain. So it has a transition matrix, and that transition matrix can be diagonalized using Fourier transform. Okay, so that's how the Fourier transform entered into the play. That you can diagonalize the transition matrix, and if you diagonalize transition matrix, it means that you can compute powers of the transition matrix. Okay. So this is something we probably will do during the course. Okay, so at least some computations for some examples. So proposition so xn is a Markov chain. Okay? So there are various ways to prove that. So probably the easiest way to prove that is to use the chain formula. Okay? So remember that according to the Ionescu-Tulsa theorem, the chain formula characterizes the Markov chain. Okay. So if a process satisfies the chain formula, then the process is a Markov chain. So remember that the stochastic process, okay, so this is something you always have to remember, is just a fancy name for sequence of random variables, okay? So it's not something to be scared about, okay? But so you given a stochastic process, if it satisfies the chain formula, then it's a Markov chain. So let's do the proof like that, no? Okay, so let's say let's take some natural number. And then let's take some points on the vertex set, okay, so on the group. So remember that the Markov is starting at x0. So here I'm taking the same x0, okay? Okay, so actually I should write like this, no? Because x0 is already chosen down there. So the chain formula gives us a formula for this in terms of the transition matrix, okay? So now what we're going to do is that we are going to compute this probability using the definition there. Okay, so this is so we can write this as a conditional probability, no? So times the same probability, times the conditioning, no? So this is, so remember, no? Okay, let me write it somewhere. No, so you just remember, no, that the probability of A given B is equal to the probability of A intersection B divided by the probability of B. Okay? So if you pass P of B to the other side, we get this formula here. Okay? So this is just by definition. But of course, we had to let me see. No, we don't have to assume that, no? So in principle, this formula here is true if this probability here is different from 0. But when we write it like this, we don't need to care about that. Because if this probability is 0, then this probability is also 0. So the identity still holds. Okay. This one doesn't hold when this guy is equal to 0 because this quotient is not well defined. But once you pass to the other side, both sides are well defined when even when the probabilities are equal to 0. So we don't have to care about that. Okay? So what is this probability? So, well, by the definition there, what is the probability of seeing this guy at the next step, given all the other steps? Well, you just have to throw your coin and get the right generator. So it's going to be nu of So I want xn to be equals bn minus 1. What is the notation? N. It's bn times xn minus 1. This is the relation I need to, it needs to happen. So if this is true, that means this bn is equal to xn times xn minus 1 to the minus 1. Okay? And then you have the other probability there. So I'm going to write the other probability there. I'm going to do again this conditioning thing. And well, we can iterate. Okay, so here we can iterate, or so it means you can do some points here. The right way to do this is induction. Okay, this is not formally, it's not mathematically completely correct. Okay, so what you really do is that you postulate that the formula I'm going to get is true, and then you prove it by induction. Okay, but when you are doing a lecture, it's better to do it this way, because then you actually discover the formula. Okay. So you discover that that probability there satisfies this formula here. Okay? So it actually satisfies the chain formula. So we need that the y is equal to b times x. So if you want to pass from x to y in this random walk, you need to select b such that this is true, right? So this means that b is equal to y x minus 1. Okay, so this is the definition of the transition matrix of the random walk on the group. Yes? Bom, nesse caso a probabilidade de x0 igual a x0 é 1. Então aqui tem um extra na fórmula da cadeia, não? Então nesse caso particular não é necessário escrevê-lo porque é 1.
Ali, só para esclarecer, os BIs, eles são as observações, né? Não são os variáveis aleatórios. Parece que BI e BD parece que eles são escolhidos através da variável aleatória é o tal. Eles não são as variáveis aleatórias, são as observações, né?
Não, esses aqui são os lançamentos de moeda.
Eles são escolhidos através de uma variável aleatória dependente cineticamente.
Então, quando eu lanço a moeda, eu escolho mais menos 1 com probabilidade P e Q, não? Então, esses são os Bs. É a sequência de lançamentos de moeda. Aí depois, o passeio, cada passo do passeio é função do ponto anterior e o lançamento da moeda que eu fiz. So this is a Markov chain, okay, with this transition probability P. And so we have lots of new examples now, right? Because, okay, so you can have a lot of fun looking at these generators and looking at the corresponding random walls there, okay? So so let me do the following now. Let me do the following observation. So now we're going to say that x is a neighbor of y if and only if y x minus 1 belongs to B, or x minus 1 y minus 1 belongs to B. Okay, so the random walk on the group can jump between x and y if and only if this probability here is different from 0, right? So a necessary condition for that is that this number here belongs to B. It's not a sufficient condition because here I'm not assuming that all elements on V have positive probability with respect to the probability distribution nu. This is usually what we do, but not necessarily included in the definition. So one has to be careful about that. So I cannot define that x is a neighbor of y with this only condition here, because this condition here is not symmetric. Okay? So I had to symmetrize it somehow. Okay? So I add this condition here below in order to make this condition here, the neighbor relation, into a equivalence relation, right? No, it's not an equivalence relation, no. It's just a symmetric relation. Into a symmetric relation because the edges are not directed on our definition of graph. Another observation, I'm not excluding the possibility of the identity being element of B. In the examples I gave you, the identity is not there. Well, the example I just erased about the random walk on the lattice. But for example, in this example here, as you can see, the identity is included, right? Because I included the transposition I, so which is just the identity. It doesn't do anything. It exchanges I with I. So it doesn't do anything. Yeah?
A gente, naquele caso de vizinhos, a gente está considerando um caso geral, a gente está considerando que ele sempre vai poder ir e voltar, ou...
Não, o que eu estou dizendo é, a primeira condição é a condição necessária para poder ir. Mas eu não necessariamente não vou poder voltar, porque esse conjunto aqui, para eu poder voltar, quer dizer que aqui no conjunto de geradores eu tenho que ter o inverso do elemento de um elemento. Ou seja, todo elemento tem que ter um inverso também aqui, que é o caso no passeio aleatório no... Como chama essa coisa? Na grade, não? Na rede inteira. Mas, por exemplo, aqui, nesse aqui, você pode ir e voltar. Porque, na verdade, toda transposição, ela é... Como chama isso? Tem um nome, esqueci. Mas, se eu aplicar uma transposição duas vezes, eu tenho uma identidade. Não, ou seja, a inversa é ela mesma. Aqui, por exemplo, você não pode voltar. Não, porque ou você faz, se você tem aqui um baralho, o que é 1, 2? É trocar as duas cartas de cima uma pela outra. O que é esse 1, 2, N? É pegar a primeira carta e colocar no final. Então não tem a inversa. Mas se eu quiser desenhar um grafo associado a isso, eu tenho que colocar a inversa, né? Porque o grafo, os elos no grafo não são orientados. Então, se eu colocar um tracinho de x a y, eu também tenho que colocar um de y para x. Apesar de que isso aí tenha a probabilidade de 0. Que você só pode pular para vizinhos. E simétrico vai ser quando você escolhe um vizinho uniformemente ao acaso. Então, com essa definição de vizinho, o passeio ele não vai ser sempre simétrico, mas sempre vai ser simples.
Ali então é simples, né?
Onde? No S? Sim. Quando você escreve SRW, é sempre simples.
Se não vai ser simétrico, vai ter que ser simples, né?
Exatamente. So let me write that an next observation. So this graph here, okay? So this graph here has a name. It's called the Kelly graph. Okay? And so let me draw here a Cayley graph. So what is that? Do you know what is that? So this is the Cayley graph of the diagonal group D6. So you have to have a little bit of imagination, but on top you have all the rotations of your favorite polygon. On the bottom you have the rotation of your favorite polygon, but rotated, no? So you can verify that this transition here is equivalent to multiply by A. So this here means multiply by A. If you multiply by A again, you go up because A squared is 1. And if you multiply by B, you go around the hexagon. So whenever you multiply by A, you go down, no, to the other side of the hexagon. And whenever you multiply by B, you go around the hexagon. Okay? So this is an example of non-trivial Cayley graph. You can have fun trying to draw these Cayley graphs here. So you can try for maybe for S4 because S4 has only 24 elements. Yeah, so maybe the drawing is possible to draw it if you have a sufficiently big piece of paper. Yeah?
Tem uma dúvida com notação. Quando você escreve uma observação, você pode induzir um grafo, ver aquelas arestas, e você escreve o random walk e bota a sequência. A lei de probabilidade dessa sequência é a mesma que era no grupo, mas aí você não tem um meio necessariamente.
Não tem um meio necessariamente. Então, o meio vai ser quando o passeio aleatório é simples simétrico. Quando eu escrevo simples só, quer dizer que a probabilidade não necessariamente é um meio. Então, está faltando um S, quer dizer que a probabilidade é qualquer. Então, aqui, por exemplo, eu tenho que escolher, não? Eu tenho que escolher com qual probabilidade eu vou rodar e com qual probabilidade eu vou virar. E, por exemplo, aqui faz sentido escolher essas duas probabilidades de forma diferente. Sim.
Então eu posso sempre ir e voltar, certo?
Sim.
Os caras que são meus vizinhos, mas tem outros geradores em B que não são meus vizinhos.
Não, os geradores são esses dois.
Mas eu não posso eu não posso induzir esse grafo em qualquer grupo?
Em qualquer grupo. Ou seja, dado um grupo e dado um conjunto de geradores, isso induz um grafo. O mesmo grupo com conjunto diferente de geradores induz um grafo diferente.
Sim. Então, a minha dúvida é a seguinte, se eu tenho um grupo de geradores e dentro desse grupo de geradores eu não tenho o inverso de algum deles, quer dizer que eles não vão ser vizinhos?
Não, vão ser vizinhos, mas você só vai poder andar naquela lista numa direção, não vai poder voltar.
Okay.
Então, por exemplo, aqui, nesse grupo aqui, ou seja, nesse grafo aqui, eu posso ir para baixo e rodar só em uma direção. Não posso rodar nas duas direções. Tá bom? Então, se eu estou aqui, a princípio eu tenho 3 vizinhos. Mas como que eu vou escolher? Eu vou jogar uma moeda e vou escolher ou rodar para lá ou descer. Mas eu não vou escolher, não posso escolher voltar na rotação. Continuando com esse exemplo aqui, note-se que aqui embaixo a rotação vai na outra direção. Tá bom? Então, aqui em cima eu posso rodar nessa direção, aqui embaixo eu posso rodar na direção oposta. Eu podia, aqui, por exemplo, isso está muito complicado, vamos botar o inverso também. Pode. Porque você pode escolher o conjunto geral que você quiser. Não tem que ser um conjunto minimal, pode ter coisas a mais. Okay. So now, I wanted to introduce this example of random walks on graphs because it allows us to start to talk about to give us a lot of examples to see some properties that are important. And to see how can we impose these conditions in a simple way. Okay, so what I want to start to talk about now is about irreducibility. Irreducibility. Okay. So there is a definition. Okay, so from now on, in almost all the definition, propositions, theorems, lemmas, exercises, etc. that we are going to do, there is a big sentence at the beginning, which I'm not going to write down, no, which is let Xn be a Markov chain of state space omega, initial law mu, and transition probability p. Okay? So that very long sentence, it's at the beginning of all definitions and theorems and propositions and etc. that we are going to do. And I'm not going to write it down because it's always the same and it's too long. Okay, so definition. So a Markov chain is irreducible if so I'm using this, usually I'm using this parenthesis to put some comment which is not necessary. Okay? It's just a comment. There exists some number L, natural number L, and points on the, okay, so the state space is not V, no, it's omega. Okay. So here we are talking about general Markov chains, not necessarily random walks. No, usually random walks, they live in a graph, therefore we call the state space V. But when it's a general Markov chain, the state space is omega. Okay. So there exists L and N and such that so three conditions are satisfied. Okay. The first is that x0 is x. The second is that xl is equal to y. And the third one, which is the important one, is that the product from I equals 1 to L of P xi minus 1, xi is bigger than 0. Okay? So this is what we call an irreducible Markov chain. What does it mean? It means that given any 2 points x and y of our state space, I can always find a path between these two guys, finite, no, such that all the steps in the path have positive probability with respect to the Markov chain. It means that there is a chance for this path to happen, right? Because this probability here is exactly the probability of being at x at time 0, arriving at y at time L. Okay? So you can always go from one point to another in a finite number of steps. So this is what we call irreducible Markov chain. Okay? So all examples I gave you, no, except maybe the Erdos-Renyi, are irreducible, right? Okay, so let me see if I have my, so let me take my, o que eu vou fazer? Esqueci. Ah, sim. Random.org, right? So let us take our favorite, I don't know if it's your favorite, maybe there is something better, no? But random.org, my probability generating, random generator number. Okay, so let's draw so let's say 5 is maybe too small, so let's do 7. Okay, so we have 7 points here, so we have a graph, or we have a state space with 7 points. And what I'm going to do here is I'm going to start to draw directed edges between these guys. Okay, so these direct edges indicate that the probability of going from one point to another in that direction is positive. No, it's not undirected edges. Up to now we are only drawing undirected edges without specifying on which direction we can travel. Okay, so the gain will be to stop at the first time we get an irreducible Markov chain. Okay? So the first one is 4, 1. 1, 2, 3, 4. So it's 4, 1. 1, 2. And just so the second one is 5, 5. Okay, that one doesn't add a lot of stuff to our thing. 5, 2. 1, 7. So one 5. 1, 5. So I'm going to stop the first time we get arrows coming out from every point. And we'll see what happens. 7, 1. 7, 1. 2, 5. 2, 5. So we still don't have points going out from 3 on 4 and 4, 6. Okay, so we're going to stop the first time that happens. Okay, 1, 6. 1, 6. 6, 4. 6, 4. 2, 3. So there's still nothing coming out from 3 and from 3. No, it's the only one that is missing for the moment.
No, it's 5 as well.
5.
There's no. Oh no, there
There's-
is 5 is 2. Yeah.
And here is also a double arrow. So there is something missing from 3, no? 4, 2. 4, 2. 2, 5. 2, 5 is already there. 3, 3, 1. Okay, now we have arrows going out from everybody. So did we get a connected graph? Well, it looks connected. So can we go from every point to any another point? Okay, you are super fast. I'm going to believe you. Okay, so this is actually an irreducible Markov chain. So this one is irreducible. So this one is irreducible. Yeah? É porque aqui tem seta para os dois lados. Do 5 para o 2.
É bidirecional essa rápida?
Tá. So, what do you think? Is always going to be irreducible if we do this? Or if we do this procedure again until the first time we get one arrow pointing out.
Yeah.
Yes.
If they are like if they're not apart, like you.
I mean, there is one. For example, if you get something like
You could get to
everybody pointing to 1, so there's a finite probability of not having a connected irreducible graph. So if, for example, if all of the guys point from, if you got all the arrows from x to 1, including the loop at 1, so you have something going out from 1.
You don't need to take a look. You can go from one to another one.
Yeah, also, yeah. So there is a positive probability of this graph not being irreducible.
You can have also like 2 circles, but they're
Yeah.
not.
Yeah, you can have also that. No, you can have lots of possibilities. In fact, any graph has a positive probability of appearing in this algorithm I just did. Okay, but there is a very beautiful theorem that tells you that the probability is very, 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 very small. Okay, it's because what I just did it's an instance of this Erdos-Renyi type of graphs. Okay, so the thing is that so this is something you can do afterwards. So how many times I had to do this random procedure to get an arrow going out from every edge, from every vertex? So if you think about it, it's what is called the coupon collector problem. So what is the coupon collector problem? It's like, it's like this the World Cup albums, no? So you have the World Cup album, you buy these envelopes, and then you open the envelopes, and then there's a probability of what is the probability of getting a new player on your album. Okay, so the probability is the number of players left divided by the total number of players. Okay, so the first one is going to be new with probability 1 because you don't have any player in your album. You put the first player, then the second player has probability n minus 1 divided by n to be a new one. And if you do the computation, this is a very nice exercise. You can check it on the books. It's discussed in detail in Levin WILMER and also in the other references. It's the number of times you had to draw a new player from these envelopes is n log n. So it's very close to n log n, actually. It's not only the order of n log n, because there is no factor in front of it. So it's not only of order n log n, it's n log n plus something of order n. So it's very concentrated about n log n. So it means that here you have to draw n log n arrows. And n log n is the threshold on which the Eros Ragni becomes connected, fully connected.
E aí vai ser reduzido.
E aí vai ser reduzido. And that means that the Markov chain is going to be reduced. Okay? So you can have fun playing with this and trying to get drawing this sort of random procedure and see how many times you have to do it until you get something non-irreducible.
Você chega numa distribuição de probabilidade, aí você chega nessa ordem aí fazendo o que é aproximando o estilo.
Isso. Bom, você pode ver no livro, tem todos os detalhes feitos. So this one is irreducible, okay? Okay, so let me see what is. So maybe I'm going to draw another one, okay? Just for fun. Smaller one, so we have bigger chance to get it non-irreducible, okay? So let's see what happens. So let's go. It's 3, 4. 1, 2, 3, 4. 3, 5. Okay, this is the bad one, right? 3, 2. Oh, this is the bad one, yeah. 3, 3. Okay, that doesn't matter. 4, 1. Actually, this is not the bad one. No, the bad one is the other way around, then. 4, 5. No, this is not a good one, no. Okay, if we got something 3, then we're done, no? It's going to be 5, 5. 3, 3. No, that is already there. 1, 4. So this is okay. So let's draw a. So we don't get lost, okay? So these ones are all already there. We're only missing one outer arrow at 2. 4, 2. 4, 2. So there's nothing getting into 3. So if we don't get anything into 3 before we get something out of 2, then we win. 4, 2. That is already there. 1, 4 is already there. 1, 4. 4, 4. 5, 1. 5, 1. 5, 1. 1, 2. So now we need something out of 2, right? 1, 1. 4, 5. 4, 5 is already there. 1, 4 is already there. 1, 4, already there. 5, 5. Of course, we are going to repeat around n minus 1, n log n minus 1 times, no? So it's a lot of times that we're going to repeat things, no? 1, 5. 1, 5 is new. 4, 3. Oh, it's going to be reducible. 2, 3. Oh, just for 1. Okay, so this one is irreducible. Well, as you may see, it looks super irreducible, no? So you can have fun at home trying to make it reducible, no? So there is something I'm not going to talk about, but you can read about in a, so it's an extra topic. Communication classes. So communication classes. So what is a communication class? So this is an extra topic. I'm not going to talk about a lot about it. So, but if you're interested, you can read it. This is you can read about it in the book by Norris. Okay. So the definition is the following. Okay, so if x and y satisfy this definition here, so notice that this definition is reducible for every x and y, but you can ask whether two particular x and y satisfy this condition. So if x and y satisfy this condition, we say that x goes to y. Okay, and we use this symbol here. And if there is a allowed path from x to y, like explained in this definition there. If x goes to y and y goes to x, we say that and we read this thing here as this symbol there means communicate with y. Okay? So this is the definition of this symbol here. So in the context of percolation theory, so this is something that people talk about it's a very important field of mathematics, of probability. We say that x and y are connected if this happens. Okay, so this is what the symbol here means. In the context of Markov chains, we say that X communicates. So communicates with Y. Okay? So the observation that one can do is that this relation here is an equivalence relation. Okay, so what does it mean, the equivalence relation? It means that it's symmetric and associative, right? So if X communicates with Y and Y communicates with Z, then X communicates with Z. Now this is more or less obvious because you can just concatenate the corresponding paths. And it's symmetric by definition. So whenever you have an equivalence relation, notice that okay, so when you talk about equivalence relation, usually you add an extra condition that it's X is related with X. Okay? Here, I'm not going to assume that, so let's say quasi. Equivalence relation, okay? Because it doesn't, this relation here does not satisfy X communicating with X necessarily. No, because if all the arrows point out from X, you cannot go back to X. Then, when you have an equivalence relation like that, you can divide your set into equivalent classes. Without the how is it called that one? The relation that when X is is related to X has a name, I forget. Reflexibility, no? Without reflexibility, the equivalent classes do not add up to the whole set. But you still can define equivalent classes. Okay? So So those are the communication classes, okay? So I'm going to just give you one example, a simple example. That I used to call the Vincennes ring graph. Okay, so we have an inner circle on which you can go in both directions, and we have other guys that can only go to the inside. And what happens here is that you have only one communicating class, which is this one. Okay. The inner ring is the only communicating class. And there are some simple theorems that you can show. So in a finite, for a finite Markov chain, there is always one communicating class. And when you send t to infinity, the probability law of the Markov chain converges to something concentrated on the communication classes. Okay, so if t is very big, you cannot be here. In fact, in this particular example, you're going one step to the inside. So if t is bigger than 1, you cannot be at the outer part of the graph. So you can complement this communication class with you can complement this graph with this outer ring. So now we have two communication classes, right? The other one and the inner one. And what happens is that for a while you stay on the outside, and then at some point you go to the inside and you never go back. So in some vague sense, at the beginning, a Markov chain moves between communication classes. And at the end, the Markov chain only moves inside communication classes. Okay? As you may have noticed here, there is a very rich structure that you can have looking at communication classes of Markov chains. But the problem is that it's too rich. Too rich means that we cannot really prove general things about that. Okay? This is why in an introductory course, we just forget about communication classes, because the dynamics in these communication classes is too complex to be described by general principles. Okay? So, but it's still a very interesting subject. You can read more if you want about it. So, the other day, so João was telling me when he did the, because João, I think he did Markov chains with me some years ago. She was reminding me that when he did the course, I told the students, no, so someone asked this question, what is going to be at this exam? So, well, it's very simple. In the exam, there will be what we did before, what we're doing now, and what we will do after the exam too. So in particular, it might be that I decided to put something about communication classes in the exam. But if it is the case, it's going to be a very guided problem. Okay, so all the definitions will be there, so you don't really have to learn beforehand about communication classes. But the point is, communication classes is a complex subject. We're not going to touch it now. If you want to know more, I think Norris it's a good reference for that. Okay? So see you on Thursday, right? And remember that next Tuesday, there's no lecture, and because of that, I moved the exam one day, one lecture up front, so I moved it to the 29th instead of the 27th. Okay?